Welcome to the Future Lab. I'm your host, Matthew. Today, we're diving headfirst into the fascinating world of large language models, or LLMs as we'll call them, and their increasingly sophisticated robotic counterparts, autonomous agents. We'll explore how these powerful tools are revolutionizing chemical discovery. It's an exciting time to be in science. Autonomous science is transforming research, combining AI and robotics to dramatically accelerate experimental processes. Think faster drug discovery, more efficient materials science and the possibilities are enormous. But how exactly are these machines taking over some parts of the research process? That's the burning question we'll tackle today. We're focusing on a recent review paper that gives a great overview of the current state of LLMs and autonomous agents in chemistry. And to make things even more meta, this episode's script was AI-assisted. It's a testament to how AI is not only advancing scientific discovery, but it's even contributing to podcast production itself. It's amazing how far things have come. So, to get started, let's look at the big picture, the state of LLMs and autonomous agents in chemistry. What are the core concepts we should all understand before we go deeper? The core idea is this: large language models, initially created for analyzing human language, are now being trained to understand the language of chemistry. Think of chemical formulas and reactions, all those symbols and structures. We are able to translate it into a format that LLMs can understand. And what does this translation achieve? Well, it unlocks an incredible array of possibilities. LLMs are showing promise in molecule design, predicting their properties with amazing accuracy and precision, and even guiding the synthesis process itself. This all ties into the concept of autonomous agents, essentially, LLMs coupled with a toolbox of other tools. Imagine an AI that can not only predict the best molecule for a given task but also plan the steps involved in producing that molecule, then perform the steps, and analyze the results all automatically. Exactly. These agents can potentially do this by autonomously searching online for synthesis procedures, accessing experimental data, even controlling robotic lab equipment. It's a real game changer for chemical discovery. That's a fantastic overview. Now that we have a basic understanding of the goals and potential, let's dive a little deeper into the nuts and bolts. Let's look at how these LLMs and agents actually work. So, we're discussing the paper, A Review of Large Language Models and Autonomous Agents in Chemistry, by Ramos, Collison, and White. A key goal was to really assess where we are with LLMs and AI agents in chemistry, and beyond, and what the future might hold. This research is incredibly important because it tackles a major bottleneck in scientific discovery: the speed and efficiency of experiments. Traditional methods can be incredibly slow and resource-intensive. The core idea is that LLMs, which are usually trained on vast amounts of text and code, are now being adapted to understand the language of chemistry. This means teaching them to interpret and generate chemical formulas, predict molecular properties, and even suggest synthetic pathways. It's not just about understanding existing chemistry, but also about enabling predictions. This is how we move towards much faster discovery of new molecules, predicting their behavior long before we even try to synthesize them. And it's not just about the LLMs themselves. The paper delves deeply into the potential of LLM-based autonomous agents. These aren't just standalone LLMs, they're essentially LLMs given access to a much broader set of tools and the ability to autonomously interact with their environment. These agents can do things like search existing literature, interact with robotic systems in a lab, plan complex syntheses and, potentially, even interpret the results of experiments, all without direct human intervention. So, the review provides a comprehensive overview of the current state of the art, highlighting both the impressive progress and the very real challenges that still remain. This seamlessly leads us to the next part, a closer look at the technical details behind LLMs and how these agents are actually built. Now that we've covered the high-level goals, let's get into the technical nitty-gritty. The review paper explores several LLM architectures, but at the heart of many of these models is the transformer architecture. This architecture is built around the concept of attention mechanisms. Can you explain what that means in simple terms? Essentially, the attention mechanism allows the model to focus on the most relevant parts of the input data. Imagine reading a sentence. You don't pay equal attention to every word. The transformer learns to do something similar, weighting different parts of the input sequence to make better predictions. And within the transformer architecture, we see different model types. There are encoder-only models, like BERT, which are great for tasks like property prediction. They extract information from the input sequence. Then there are decoder-only models, like GPT, which are fantastic for generation tasks, such as creating new molecules with specific properties. They predict the next token in a sequence, making them ideal for creating novel structures. And finally, there are encoder-decoder models, such as BART, which combine the best of both worlds, making them adept at sequence-to-sequence tasks like predicting the products of a chemical reaction from a given set of reactants. So, it's not just one-size-fits-all. The architecture of these models is chosen depending on the specific chemistry task they need to perform. This flexibility is a huge part of the innovation. Beyond the basic model types, we also see considerable innovation in multitask and multimodal models, which can handle multiple tasks or different kinds of data simultaneously. That's a huge leap forward, right? Absolutely. Imagine a model that can not only predict properties from a chemical formula but also generate a natural language description of that molecule, or even interpret an image of its spectral data. That's the kind of power these multimodal systems are starting to offer. Another important aspect is the use of self-supervised pre-training. This is where the model is trained on a massive dataset of unlabeled chemical data, like millions of chemical compounds and their structures, before any task-specific training is performed. This method is incredibly efficient, allowing the model to learn the underlying patterns and rules of chemistry before it even begins to learn the specific task of property prediction or reaction prediction. It's akin to a child learning the basic grammar of their language before learning to write a poem. But the review also highlights some challenges. Data quality, for example, is a huge issue. If the training data is inaccurate or incomplete, then so will the model's predictions be, and the lack of standardized benchmarks makes it hard to compare different models directly. We need a better way to measure how well these models perform against real-world tasks, to see where there is still room for improvements. Exactly. All these considerations, the model architectures, the innovative training methods, and the ongoing challenges, perfectly set the stage for our next discussion, the real-world applications and potential impacts of this research. So, we've explored the technical side, now let's shift to the exciting implications. The applications of LLMs and autonomous agents in chemistry are truly transforming the field. Let's start with property prediction. How are LLMs improving this critical aspect of chemical research? LLMs are making property prediction faster and far more accurate. Chemists can now predict the properties of molecules, things like solubility, toxicity, reactivity, with significantly less reliance on expensive and time-consuming wet lab experiments. This is a huge boon for drug discovery. Imagine being able to screen millions of potential drug candidates in silico before ever synthesizing a single molecule in the lab. That's the kind of speed-up we're talking about. And it's not just drug discovery, materials science also stands to benefit massively. LLMs can help design and identify novel materials with specific properties, like high temperature stability or exceptional conductivity. Absolutely. And then there's inverse design, where the goal is to create a molecule with specific properties. Here's where decoder-only LLMs really shine. These models excel at generating novel molecules based on desired properties. They can explore a far wider range of molecular structures than traditional methods, opening up completely new avenues for drug design, materials science and catalysis. That's an enormous leap forward, in terms of innovation. It's no longer a matter of modifying existing molecules, LLMs can actually design entirely new ones from scratch. Of course, synthesis is still vital. How do LLMs help here? LLMs can optimize synthetic routes, the steps taken to create a molecule. By analyzing vast databases of chemical reactions, they can suggest the most efficient, cost-effective, and environmentally benign pathways to synthesize the desired molecules. This is especially helpful when dealing with complex molecules. Finding the right path can be a real challenge, and LLMs can help to significantly reduce the trial and error effort. But the real revolution, in my opinion, comes with the integration of LLMs into autonomous agents. This is where we're starting to see machines take on some of the experimental tasks themselves. These agents aren't just confined to computer simulations. We're talking about AI controlling robotic systems in a physical lab setting. They can plan and execute experiments, analyze results, and even adjust parameters automatically. Imagine a fully automated lab running experiments 24/7, constantly refining conditions and generating new data. That isn't some far-off futuristic fantasy, it's getting increasingly closer to reality. It's truly remarkable. The review paper isn't just describing a technology, it's showing how the foundation for a revolution in experimental chemistry is already being laid. This brings us to the last section, where we'll consider the future implications of all this progress. So, to wrap things up, let's revisit the key takeaways from this fascinating review. The research clearly shows that LLMs are becoming incredibly powerful tools for chemists. We've seen how effective they are for property prediction, accelerating the identification of promising molecules, speeding up inverse design to create entirely novel compounds, and optimizing synthetic pathways to make production more efficient. The integration of LLMs into autonomous agents is truly game-changing, pushing automation into the laboratory itself. The potential to automate experiments, analyze results, and continuously refine conditions is truly revolutionary. It's a huge step towards realizing the dream of a fully automated laboratory, a facility where AI agents run experiments around the clock, significantly accelerating the pace of discovery. But, of course, we have to acknowledge the challenges. The reliability of these systems hinges on the quality of the data they're trained on. We need better curated datasets, more robust benchmarks, and better ways to interpret how these models are making their predictions. And, critically, we must consider the ethical and safety implications of this powerful technology. This isn't just about speed, it's about responsible innovation. This review underscores a future where LLMs and autonomous agents will become indispensable tools for chemical research and development. The potential to accelerate innovation, streamline workflows, and ultimately lead to truly autonomous laboratories is immense. It's a future where human ingenuity and creativity are augmented, not replaced, by AI. The human in the loop is crucial for validation, oversight, and ensuring that the technology develops and is implemented responsibly. So, what's next? The authors of this review, and the broader research community, have pointed out several areas for ongoing work. We need improved datasets, stronger benchmarks, and improved methods for interpreting and controlling these powerful tools. Thank you for tuning into the Future Lab. This episode's script, as a reminder, was AI-assisted, a perfect example of the kind of automation transforming our world. We appreciate your time and always welcome your feedback. Until next time, stay curious.